Je disais, le partage sur YouTube, ça fonctionne, vous avez vérifié?
Normalement, c'est automatique. Je peux aller vérifier, mais
J'ai juste regardé, c'est automatique et c'est bon, ça y est.
ouais. Ok.
C'est live.
Ouais, c'est bon.
Okay, so maybe we start and the laters will join ongoing. So welcome everyone. My name is Jeremy Blair. I'm a professor at École nationale des ponts et chaussées in Paris. And I'm very happy to introduce this new conference cycle of the Executive Master of Digital Twins for Infrastructures and Cities. So the idea of this conference cycle is to invite different people to come and speak about digital twins for infrastructures and digitalization in general. And so we'll try to have one event like this, one per month approximately. So welcome everyone who joined this seminar or who are watching live on YouTube or on replay. So it's always a pleasure to have you with us. And so today we will start with the first event. The talk will be given by Ayub Karwit, who is working at CETEC ITS. So Ayub is a civil engineer with a master's in building information modeling, and currently is working with on the project Grand Paris Express, which is this big metro line around Paris. So one of the most the biggest project of metro infrastructure in Europe currently. And so he's working as a metro rail systems construction manager for this project. And so we are very happy to have Ayub with us today to speak about how digital twins can enhance metro infrastructure reliability and resilience. So thank you again, Ayub, for being here. So you have the floor for approximately 40 minutes, 45 minutes, and then we will have a few questions at the end. Thank you again.
Thank you very much, Jeremy. Thank you, Mathieu, for this invitation. And I would like to congratulate you for the success of this program, first of all. And then let's kick our presentation. So, as you see, the topic of my presentation would be about enhancing metro infrastructure reliability and resilience through digital twin innovation, which means that I'll be talking about how digital twin can be like efficient and can solve many problems for complex projects like a metro infrastructure, especially for maintenance. So I'll present to you the table of contents so as to know what I'll be presenting. So I'll start by a general presentation of the project where I work, which is the Le Grand Paris Express. Then I'll try to talk about maintenance challenges and context of metro infrastructure, how we do maintenance and the challenges that we face every day. Then I will try to talk about methods or maintenance methods that we use to face those challenges. Then we will talk about the solution like the digital twin, which comes with a new solution so as to do maintenance in an efficient way. Then we'll talk a little bit about the brain of this digital twin, of this like digital solution. Then maybe talking about some practical use cases in metro projects. And I'll try to end my presentation with like the benefits of 3D models and BIM in general. Then we'll talk like in a general way about implementing a digital twin in such a complex projects like a metro infrastructure project. And of course, we'll conclude our presentation with some visions. First of all, I would like to present myself before like we start. So Ayub Kawit, I'm a civil engineer, as you see, with some modest experience in BIM, 3D models. I have 4 years of experience into this project, which is the Le Grand Paris Express. And now I am a metro rail system manager. And as you see, I love data systems and think things that actual align. Um, so our first point is the presentation of Le Grand Paris Express. As you see here, I put the map of the project. As you see, we have too many lines that are under construction around Paris. As you see here, we have Paris here, and then the other, like the region of Paris, out of Paris. We will try to put some lines so as to solve many like traffic problems. And as you see, we have four new lines. We start from the 40. That we will have a part of the extension of this line that exists nowadays. Then we will have the new metro line, which is 50, 60, 70, 17, sorry. Then the 20. The whole project is about 200 kilometers of new fully automated metro lines under construction. We have four new lines, 15, 16, 17, 18, then two line extensions, 11 and 14. We don't see the 11 here because it's not like decided yet. It's just an idea for the moment. Then we will have 68 new stations connecting key urban and business districts. Then I would like to talk to you about the infrastructure that exists before the new project, which is Grand Paris Express, which means that as you see here, we have the metro lines that existed from a long time ago in Paris and around Paris. We have 14 metro lines, 303 stations, and 225 kilometers of track operated by RATP, which is RATP. It is the operator and the maintainer of the ancient metro project around Paris. And as you see, 225 kilometers of ancient metro traffic or lines is the equivalent of the new project that we are constructing now. Besides, we have 5 regional trains interconnection with metro and suburban rail area of Paris. As you see, for traffic, we have 9 million passengers by day. We have one station every 550 meters. We have some ancient infrastructure, as I mentioned, like from 1900. We have 1970 with partial automation, of course, because the difference between the new metro project and the ancient one is that the new one is fully automated. So now I'll give you an idea about some stations of the new project so as to give you like a whole view of what we are constructing now. As you see, this is one of the biggest stations that we have in this project, new project. It is called Saint-Denis-Pleyel. Here we have the conception, and here we have the real project, which is now like functioning, which is working now. It is open for one line, and actually this station will like receive too many metro lines and too many regional trains. Then present to you this station, which is Institut Gustave Roussy. As you see, this is the 3D model of the station. Then this is the rail station, which is like open now for one line. And actually this station will receive two lines at the same station. Then we have this one, Noisy-Champs, which will receive two lines, yeah, of metro and some regional trains. As you see, this is the conception and this is the real state of the project now. So let's let's go now into our topic. So the maintenance challenges and the context. As I said, talking about the table contents, the metro infrastructure actually faces too many problems and challenges because of the complexity of the project. We talk about 200 like kilometers of metro infrastructure. Of course, that will have too many stations, too many traffic, too many people using those this infrastructure. So of course that we will face too many challenges, and the maintainers will be facing too many problems and challenges, and those challenges actually um, are like presented on into 4 points. As you see, we have some asset like interdependency, which means that all the components are connected to each other, which means that this one like presents a big difficulty for the teams of maintenance, which means that whenever we have a problem into one component, one equipment that will affect the other components, that means that we will have the whole system down, which is not working. Then we have data overload, which means the project or the infrastructure is too big, and that generates actually too much data that sometimes we can't use it in the right way, which means that we can have some information, some alerts, but we can't use them because we don't see them. Then we can talk about information fragmentation, which means that we have too many information plans, like papers, documents about components, but since the project is very complex, we have big amount of components. It's sometimes difficult to analyze, to see, to revise. Then we have the access limitations, which means that the project is sometimes very complex. Like when we have some big stations, it is a little bit hard to go and find the right component, which is down. That's why this is one of the challenges of the maintenance teams nowadays. And I'll present to you like so as to make you a little bit on those points that I've just presented. I found this figure which presents the challenges and the complexity of real project. As you see, our real project is like it has too many components, too many parts. The first one we can talk about is the source of the power, electrical power. So this first part like gives power to the trains, to the catenary system, so as to make the trains, of course, rolling and going from point A to B. And as you see, sometimes we can have some interconnections between different lines, and which makes the project or the infrastructure more complex. And this, of course, creates more challenges and more difficulties for maintenance teams. So to face those challenges nowadays, like in the majority of the projects of metro infrastructures, teams, maintenance teams are using some basic methods of maintenance. And as you see, we'll be talking about them. The first one is reactive maintenance, which I represent like a firefighting method, which means that, as you see here, which means that the teams like try to solve the problem after when it happens, and this is like a firefighting method. We try to solve problems after they happen, and it's not really efficient, and it costs a lot of money for, of course, the maintainer. And as you see, uh, It is a method which is 3 to 5 costlier than predictive maintenance. Then, as I've just said, the majority of projects still using this method. We can find some numbers that talk about 70% of real interventions. Then we have another method, which is preventive maintenance, which means that we program the maintenance, like we program some frequency to maintain some components. And as you see here, this may be a smarter idea so as to solve problems and to avoid the component problems. But the problem is that we can put out some components which are like working. And this is not an efficient way because it generates too much cost for the maintenance teams. As you see here, we have 30% unnecessary tasks, which means that we take out some components which still working. That is not necessary. We have 20 to 25% of failures occur between inspections, which means that we have some failures that happens between the inspections simply. So this method, it generates waste and wears components prematurely, which means that this is what I've said at the beginning. We can change some components that still working, and this is a big loss. So talking about those two basic methods of maintenance pushes us to look for some more efficient solutions that will helps us to find the right point, the optimized points so as to maintain, so as to know when to the right moment to maintain and the right quantity to maintain. And that's why a digital twin is here, so as to helps us to solve this problem and optimize maintenance for metro infrastructure or complex infrastructures in general. Here I put like a general scheme which presents the basics of this concept, digital twin. As you see, we have three basic and important parts of this digital twin. We have the physical environment, which is the real project, the components, the infrastructure. Then we have the virtual environment, which means that besides the physical part, we have like a modeled virtual environment, the same parts we have them in a digital environment, digital replica, we can say. Then we have the analytical environment, which is the brain that connect the physical environment to the virtual environment, which gives us like a whole view of what's happening in reality into the project or into the infrastructure, so as then to use all the information that we extract and predict what will happen and make decisions to avoid some problems. So this leads us to talk about the brain of this digital solution, which is the predictive maintenance. So we've talked about the two concepts or methods of maintenance, reactive maintenance and preventive maintenance. Now we're talking about a new concept. It is not new, but a smarter concept, which is predictive maintenance. So predictive maintenance, as you see here, is predicting when the component will shut down before it happens. And this actually is an efficient way of maintaining complex project, and it helps us like to have some optimum time to do maintenance, to predict what will happen, to give time to teams of maintenance so as to be organized, to predict the right quantity of equipments and components that we will need in the future. And this actually has a direct impact on the cost of the maintenance. So let's zoom in a little bit into this predictive maintenance, into this brain that is doing those predictions of components failures. As you see here, we have different, like this brain works according to different steps. The first step is acquiring data, which means that we put some sensors into the infrastructure so as to extract what is happening and information that is happening of what is happening into reality. Then we combine them with some generated data. This is so important. Generated data are data which is extracted from modeled system. Let's say, for example, we are trying to monitor a component into a tunnel. We have we have to prepare two type of data so as to make this brain works. The first one is the data that's coming from the sensor into the tunnel. Second part is the data generated from some digital models that we model by tools. Actually, there are too much the tools that we can use for that. We give some constructs to the same component into the tunnel, but into tools, the digital tools, and we try to follow its behavior and how it will react. And this data actually is saved so as to give it to this brain to treat it and use it for making decision. So after the data acquiring part, we have the pre-processed data, which means that this amount of information that we extract, we try to refine it. We try to get off all the noises into those signals or to those information that we extract. Then we give it to an algorithm so as to give us some decisions, which means that this part, the algorithm receive the data, a clean data, then it tries to know the behavior of our component that we're trying to follow or to track. When it's done, which means when the brain or this part, like the algorithm, knows the behavior when the component will shut down, when the component is working according to many parameters, let's say pressure or mechanical efforts or whatever, it can know, receiving eventually some other data. This brain or this algorithm can know if the component will still be working for a long time or not. And this is the point of the concept of predictive maintenance. We give it too much data of reality and modeled data, then the brain or the predictive maintenance brain should be capable of predicting the future of this component function. And then, as you see, we can be back to the sensor data, which means that the whole process, when it's done, we can put it into sensor directly, which means that the sensor can extract the information and try to make decisions at the same time and give it to teams, maintainers, and the interfaces of the team maintainers, which means dashboards or stuff like this. Here I present to you an example of data that we extract, different types of data. As you see here, we have the training data, which means in blue, which means all the data that is modeled, which means that the system or the component is modeled in a computer tool. Then we receive some results, which are the failure event data. As you see here, the blue line, this is en fait, these are results of the same component, the same system. And as you see, we have different failure events, which are practically the same if we zoom out. Here in orange, you have the current data, which means the behavior of the component that we are following in reality. And as you see, it is a little bit into the data modeled. So the algorithm, for example, at this stage can say that the component will fail here, for example, because he has some data of the points where the modeled component has failed. He can predict where the component will fail in reality. And of course, we will have this actually, this is done by some uncertainty. It's not 100% sure. We have some percentage of uncertainty, and actually the brain can give us this uncertainty. One of the key elements of the brain that predicts the future of a component is identifying condition indicators. I'll be back to my previous slide, which means that we're talking about this point. Before we give the data to the algorithm, we try to transform the data that we have processed into some indicators, into some features that helps us know whether the component will stay working or not. So, and this is actually a key point. Why? Because if it is not done in the right way, the whole decision given by the algorithm will be false, and we will be like forced to change a component in a based on information that's are not correct. As you see here, we have some data that we have received from sensors. You see too much noise here. Then we pre-process this data. As you see, we have refined the data. Practically all the noises are out. Then from this one, as you see here, we have the time. We can get the frequency curves, and those like this transformation helps us to know when the component will fail. And as you see here, the healthy operation stays it indicates that the component stays working at some frequencies, but the faulty operation gives us the information, the frequency about it gives us information about the frequency where the component is not working. So generally, the idea is that we don't give the data as it is when we extract it. We have to refine it. We have to transform it so as to identify some condition indicators. And that's actually will be a good input for our brain, our algorithm, so as to decide whether the component will work or not at some point of time. And this slide actually present to you, I'll try to explain how it works exactly, the algorithm. As you see, the data that I have just explained, which means the data refined and well treated is an input. Then the algorithm get this data so as to be able to answer these questions. Practically, this is the real work. There are three types of questions that the algorithm of predictive brain maintenance can do. The first one is answering into this one is like it tries to detect anomalies and uh, knows whether the component at the right moment it is working or not. And the question simply is my machine operating normally, which means that it's clear that the algorithm trying to find if at the actual moment if the component is working as it should be. Then the second question, what's wrong with my machine? Uh, Here the algorithm tries to understand what is going on based on what's the data that we gave him. He can like understand what is happening practically and try to then estimate some time that will be like enough for the component to shut down. And this is called the rule actually. Um, Here in this slide, I'll explain the rule estimation, which is uh, the time that remains so as to so as the component so as the component be shattered. So as you see here, we have the beginning of the measurement of the data, and the brain actually starts working, and it can detect the moment where the component will be shut down, and it can give you the time which remains so as to for the components so as to be working. And this is the whole work actually for role estimation. The brain or the predictive maintenance brain can calculate how much time still we have for that components so as to shut down. Uh, After talking about some theoretical like
What type of sensor?
sorry,
What type of sensor data it is reflecting here?
this is actually a general curve. It is like it's not linked to some specific sensor. It is just like a scheme that is explaining how it works for a rule estimation. But in general, we can have too many type of sensors. It depends actually on the digital twin that we will do that we want to create. It depends on the infrastructure we have. For example, let's talk about the let's talk about some maybe we choose a machine, for example, an industrial machine. We can put some sensors for detecting the vibration and following the vibration behavior, for example. It depends on the infrastructure that we want to monitor, that we want to follow. I don't know if my answer is clear. Okay. So after talking about theoretical ideas, I'll be talking here about some practical use cases of the predictive maintenance system and how we use it actually into complex projects like metro infrastructure projects and infrastructure. I will be talking about two examples, practical examples that we start to see like into big projects. The first one is a real switch monitor. Second one is tunnel structure. So let's zoom in the real switch monitor. I'll start by defining this. I'll start by defining this actually this component of a rail system or a whole rail system project or infrastructures. As you see, a rail switch monitor is the component which is responsible of changing the line for a train. For example, let's say we have our train at this point, and we have two choices actually. Whether the train continues into this way, direct way, then we have nothing to do. Or the train will change the line and go there. So at this time, this switch here should do some mechanical movement so as to move some parts of rail here, and like which push the train to go into this line. Here you have some practical, some real photos of those switch monitors. As you see in tunnels, we can find many different types of switches. And here, as you see in our simple tunnel, we have like switches that pushes the train to go from a line to another. We have some switches, complex switches that permit to go from like from the line A to the line C when we have too much lines at the same point. Those are like actually some complex systems where we need digital twins so as to monitor with some certainty the system. And here I have a theoretical explanation of how it works. As I have just said, we have like here two lines. This one, the straight lines, and this line, sorry. So as to keep going into the straight line, this switch motor actually should push those like switch rail into this sense. So that way the train will keep going into the same line and won't actually change its way. But if we want the train to change its way, we have actually to push the switch motor that way so as to like permit and push the train to go that way. And actually now, after describing the system, I think you can now see the importance of monitoring this whole system, the switch system, which is very, very important for every rail infrastructure. Actually, it represents only 10% of the whole rail linear, but in reality, 30% of the problems are coming from this part, actually. And so, as you see, this part, like a digital twin into this system, is a great idea, actually, so as to provide safety and security of the rail system. As you see, I present to you a solution like a scheme, a simple scheme of a solution that is like trying to solve those problems. As you see, we have too many components. It is actually the same theoretical basic ideas that we have described at the beginning of the preventive brain. So we have a brain here that catches data, a little brain, a part that catches data. Then it gives it to an analytical platform, sorry. And this analytic platform, it's like it can analyze the whole data that we have so as to make decisions and know whether we have to create an alert about this system, or we stay work with it without any problem. Here I present to you like this is an outcome of the extraction data part. This is a refined information of electrical information about the component. And as you see, here we have some modeled information, some outcomes from the model of the component that monitor the rail, which is the switch. And as you see, the algorithm can know from this data, income data, can know whether the component is working good or not. And it can predict if the component will be working for a long time or not. So let's be direct. Here, as you see, the real data. Those are data from a modeled a component into a computer. And here are real data. And as you see, those three options actually representing three results that our system of our analytical system gives us. So the first one here, like this real data for the analytical system or for the analytical platform, this first one like represents some good data, which means that the component will stay working without any problem. The second one, like the algorithm starts detecting anomalies and problems. And this one, actually, for the algorithm is a big problem, and we have to make some decisions to change the component. So those are practical information that we get from the sensors. And of course, that are like refined information, refined signals that we get at the end after processing the whole information extracted. Second practical use case of digital twins will be tunnels and station civil infrastructure. As you know, tunnels and underground stations they have many constraints every day, like some mechanical, fluid, and vibration constraints. Those constraints actually can generate many problems for the whole civil infrastructure, like cracks, like the destruction of some civil parts of the project. And this is this is a high security topic, and actually the teams, maintenance teams, has to be aware of whatever happens into the structure so as to follow what is happening and its behavior. And for that, the digital twin, of course, presents a good, efficient solution. And as you see here, we have the theoretical scheme and on how it works actually. And as you see, it is the same that we have presented at the beginning. The information that we get from the physical asset, physical object, which is the tunnel or structure of the tunnel, goes to sensors. So sensors put this information into the brain, and the brain analyze all the information extracted so as to decide whether we have a problem or not. And here, this is the same thing. I'm presenting to you actually the results that we can have for digital twin. As you see here, we can like the output is 3D vision or view about the instant behavior of the structure. Like here, we can know where we have problems or not, depending on the results that we have. Um, so now after talking about theoretical basics of predictive maintenance and some real use cases, let's talk about how 3D models actually are useful for those digital twins. Let's imagine this station, for example, is one of the stations that I have presented to you of the new project Grand Paris Express. Let's imagine the maintenance of this project, actually, of this station. I don't know if you can imagine the maintenance or the monitoring of this station with only numerical information and um, text. Actually, this is not efficient, and this kind of station can generate too much data, too much information, and this actually creates a challenge in front of the agent maintainer so as to read, to analyze, and to decide about what we are going to do. So that's why a digital twin with a 3D um, model can helps us read in a practical way what is happening at instant time, and of course that will make it easier for uh, maintenance teams. And for example, if we have a problem here in some point here with 2D like platform 2D results, we can know where is the component exactly. But with a 3D model, we can have the component in alert with a red color, which means that maybe we can have the the shortest way to arrive to that component which is damaged. So here I have an example so as to explain to you what I have just said. As you see, we have two options of outcomes uh, that's coming from a digital twin. Whether we have some texts like this, temperature, roll, humidity, and displacement of a tunnel, for example, or we can model all of those information directly on the 3D model, which helps a lot, and it permits, like, actually it pushes the maintainer to be more efficient and quicker when it comes to intervening directly into that place where the component is shut down or where the infrastructure is cracking. So yeah, after talking about those use cases, let's talk now about how we can implement a digital twin for complex or project infrastructures in general. We have many steps that we have to follow. First of all, we have to prepare the data foundation. Actually, we have to be efficient at that. Sensors, data environments, all of that should be efficient because it is the source of the whole process. It is the foundation of the whole process of a digital twin. So as to decide the digital twin should have the right information, well treated for information, well refined information, and without that, of course, the digital twin will gives us some bad information that won't helps us to solve problems, but that will create some new problems. Then we have the 3D model integration, which means that we have to prepare beside the data foundation, we have to prepare the 3D model integration. Integration is not easy. It's not like auto systematically. We have to think it before starting the construction. We have to think it from the conception of a project, of an infrastructure, so as to prepare the 3D model for receiving the digital twin incomes. Of course, we can have 3D models after constructing the project, but that will be costly. That will be with a big cost. So better be efficient and try to prepare the 3D model before constructing the project. Analytics layer. This is the third part. And actually, analytic layer, it represents the whole brain that we have into the digital twin that can take decisions. So we have to prepare at first the environment for that analytical layer, for that brain so as to work. Maybe some strong processor, maybe some good digital environment. Then we have operational deployment. As you know, every kind of, in general, whatever kind of projects we want to deploy, we have too many people that are working on this project. So one of the biggest points that we have, it is actually a human point that we have to pay attention to, is how those people, how those teams working on that project interact and coordinate things about with each other so as to have a global final result, which is digital twin. The digital twin, a complete digital twin with 3D model with a good data foundation and analytical layer, it's like requires too much expertise. And if we don't coordinate in a good way, like those expertise, we can have a weak digital twin at the end. So the last point, which is governance and continuous improvement. That means that that digital twin, when it is working, it should be like from time to time, like we have to integrate the evolutions of the project. For example, we can maybe change move, for example, a door from a place to another place into a station. That information should be integrated into the 3D model so as to help the digital twin to have all the data that is representing the real infrastructure and not a modified ancient infrastructure. So we're talking about some solution to solve a big problem of maintenance, but actually it's not that easy. We have too much challenges that like that face the construction of this kind of solution, the digital twin. We can have technical challenges, which means, for example, we can face some problems on processing the signals or the extraction of information from the real infrastructure could be a little bit hard sometimes because we can have some sensors that receives very difficult information and signals to process and to refine. Then we can have organizational challenges, which means that this is the point that I have just talked about, which means that sometimes the variety of expertises into a field, some field, especially about when we're working into complex project, we have too much expertises. So making one digital twin that represent the whole project or the infrastructure is just difficult because we have too much people working on that project, and we should really be attentional about how we coordinate and if every expertise is taken in consideration the information or the inputs of the other teams or the other expertises. Third point is cybersecurity. And this is actually especially with AI. Let's imagine we have some digital twin that includes intelligence, artificial intelligence decision making. That could like present a big opportunity for people who are attacking for hackers of course. And this is a big point, like we have to pay attention to it, because if like someone, an outsider, get in that system, that digital twin, it can have the whole control of the whole infrastructure. And if we talk about a metro system, for example, having a control of that system is not a good, it's not a good news. Like the hacker can ruin the whole project and make some damages to the infrastructure, maybe to other people, to the people using that metro. Future. So these are three challenges. Maybe we have more, but those are the most important ones. Then what we have to think about now, and what we are thinking about now, like talking about metro infrastructure, metro projects, are making like is making one digital twin tool, digital twin paradigm that like helps to monitor the whole infrastructure system. As you know, in infrastructure projects like a metro, we have a system which is called SCADA. The SCADA is a system that has the whole vision of the infrastructure, but the problem is that it actually it has the instant vision, but it can't make decisions. It can't prevent. It can't actually predict. Sorry, it can't predict the future of whatever will happen into a project. So if we take the SCADA, which is well-known concept, into a metro project, and add the touch of a digital twin, that which means if we add the decision making capability and ability with some 3D vision, 3D models, maybe that will be a perfect digital twin for an infrastructure. It will help to maybe predict what will happen, and this is a good, efficient solution so as to reduce the cost of maintenance. Or maybe let's imagine a digital twin of a metro system that predict what will happen, and then program works of the teams, of maintaining teams. So my presentation is finished here. Thank you for attention, and of course I'm here to answer your questions.
Thank you, Ayub. Thank you very much. So we have some time for some quick questions. I think that there was already one in the chat. If you have questions, please, you can either raise your hand and speak directly, or you can type in the chat your question. So there was one question about how the new lines from